Hello everybody, in this video we're going to go over the electric field. Let's begin. Alright, so the first thing that we should go over is the definition of electric fields. Okay, so it's important for us to know that all charges have their own electric field. And in fact, we will be going over how to draw the electric field. Let's move that up. E-fields are vector fields, which means direction matters. So whether you have a positive charge or a negative charge, depending on the charge, the field that we draw will also change. Now, if you're wondering, why do we even have these E-fields? Well, E-fields are there to help us predict how other objects can interact with the field or the object creating the field. So, for example, a field that we're used to is the gravitational field. So we are all within the Earth's gravitational field, okay? And so because we know that we are within the Earth's gravitational field, we know how we will interact with the Earth. And simply put, we'll just be pulled in towards the Earth. The Sun also has its own gravitational field, and because the Sun has its own gravitational field, we know how other planets will interact while it is within the Sun's gravitational field. Okay, so that's why we have fields. It's a way for us to model how other charged objects will interact. So let's begin by first going over how to draw E-fields. Okay, whenever we do these physics problems, it's very important to start off with not only sketching out the situation, but also creating any models possible to really help us out. And drawing E-fields is no exception. I'm going to go over a couple of different iterations on how to draw E-fields. Alright, so first things, it's going to resemble a lot like a free body diagram, just by the way it looks. Okay, so we're going to start off with a positively charged object. Okay, so we'll say this is a positively charged object, and the E-field that we can draw is by drawing arrows out of the positively charged object. Okay, so you'll notice that my arrowheads are pointing out of the positively charged object. Okay, so this is an example of a positively charged E-field. So if we have a negatively charged object, we can draw the E-field simply by doing the reverse. Our arrows will go in towards the object, like so. Alright, so this here is just a nice little sketch of what a E-field would look like for both a positively and a negatively charged object. Now, visually, I can tell you that these two charged objects probably have the same magnitude of charge just by the way I drew them. So let's dive into that. How can we show that the charge is a weaker charge or a stronger charge? Well, simply put, it is the density of the field lines. Meaning, the more field lines there are, the stronger the E-field is, or the stronger the charge is. So let's do an example over here. If I were to draw two different charges, right? Two positive charges here, one on the left and one on the right, and if I were to draw the E-field, let's say the one on the right kind of looks like this. Or excuse me, the one on the left looks like this, but the one on the right, it looks like this. Okay, now just by the density of the lines, which is just a really fancy way of saying how close together the lines are, or the amount of lines, I can tell you that the charge on the right has a greater magnitude. Okay, so we can say, for example, this could be like a 10 Coulomb object, and this could be like a 1 Coulomb object. All right, and the same goes for the negatively charged object on the left. I won't go over how to draw that though. All right, so we have two different ways of showing how to draw fields, but what if you have more than one charged object? How do we draw those fields? Well, simply put, let's do a positive and a positively charged object. All right, so this is what we know. Like charges repel. That is just the fundamental law of charges. And so the E-field will also help us visualize that. Now, let's follow the rules and make sure that all field lines go away from the positive charge. Alright, so here we have two positive charges, and I can show you how to draw the E-field for two positive charges. So let me show you the quick, very to-the-point way of drawing it, and then I'll go into detail of why we draw it this way. Okay, so first off, I'm going to draw the left-hand field first. I'm going to start off on the far left. Okay, so we have a far left field, and it's doing a little bit of this. Okay. Now, as we get closer to the opposite charge on the right, some very unique things start to happen. We get this bending effect, like so. Now, once again, this is how we draw it, but I'll go into the conceptual reason as to why this bending effect happens. But let's draw the one on the right. Okay, so this one goes up, goes out. Now, if you remember, like charges repel, and unlike charges attract. And so here, visually, we can see this repelling nature of two like charges. Okay, a couple of important things I want to highlight is right here in the middle. Notice that there are no E-field lines. Okay, so all the field lines there are, they actually cancel out. Okay, so this is how you would draw two like charges. Let's go into the idea of why this happens. So if I have a positive charge here, and if I have a positive charge here, now if you remember from our very beginning definition, we said that E field is a vector field. So what that means is, let's call this Q1, and let's call this Q2. So at this point right there, right in the middle between Q1 and Q2, if I wanted to draw a E field vector from Q1, it would look something like this. Okay, a little bit out like that. Now I'm not drawing it too big because it's a little bit further away. So for example, if I wanted to draw the E field vector of Q1 right here, because we're super close to the charge, the vector would be super long. Okay, it's a strong field line. Now Q2 at the same location, okay, Q2 at the same location, there will be an E field vector pointing to the left. Because remember, field vectors always point away from positives. Okay, so from Q2, it points away to the left. Now, due to the nature of vectors, here we have a vector pointing to the left.
Bus 58 has now arrived.
And here we have a vector pointing to the right. So mathematically what happens is that the two vectors cancel out. And we see that over here, where in the middle, there are no vectors left. Okay, and due to the nature of superposition, it also affects the vectors when we are, let's say, up here. So if I take a look at like a vertical point above that middle point, okay, we can see here that our vector lines are shooting upwards. Okay, and here's the reason why. So from Q1, we have a vector pointing radially outwards. So let me see if I could do a better job. There we go. We have Q1 pointing this way, and from Q2, let's see if I could do a good job there. There we go. From Q2, we're pointing radially out this way. So what this means is that we are now dealing with components. So this horizontal component that I just drew in and this vertical component for Q2 exist. Same with Q1. So Q1, we have this horizontal component and this vertical component. All right. Now, just like what happened here in the middle, these two horizontal components, okay, they would cancel out, leaving only with these vertical components. And so the net field would be pointing upwards. And we get that sense over here as we see the field lines coalescing in the upwards direction. All right? Now, what about this point right here? Okay, so let's go back to that point right there that we were describing. So I already drew the vector field from Q1, but what about Q2? Is Q2 exerting, or does Q2 have a field there? And the answer is yes. And we know it's yes because if we were to draw the vectors for Q2 like we did before, right? So if we take a look over here, Q2, or just charge, it goes straight out. Meaning that at that point, we would have a E field vector, very, very small because it's far away from Q2, that looks like that. And so with this Q1 E field vector and this Q2 E field vector, when you add them up together, we would just draw it as a vector field going straight out to the left. Okay, so there's a couple of things that we need to take into consideration. One, these E fields are actually vector lines. So if I were to draw a single charge, right? Technically, at this point here, we have a E field vector going like that. Okay, and I'll do a different color. Right above it, Okay, we have another vector going up like that. And right above that, we also have another vector going up like this. And right above it, we also have another vector going up. So what ends up happening is that all of these vectors, they add up so that we draw the model as if it's a net vector, like so. But just so you know, these Efield vectors are all of the Efields along that path added up. It's a net field. So, all right. Okay, so let's go over the idea of a positive field with a negative field. Okay, so positive here and negative here. Now, before I show you the way that you can draw it, let's go over the conceptual idea first. Let's say these two have the same amount of charge, and we're looking at exactly middle in between the two, charges. Let's draw the positive one first. So at that point, the E-field vector will be pointing away from the positive, like so. Now, let's draw a E-field vector for the negative charge at that same exact point. At that same exact point, we will have a E-field vector pointing towards the negative. Remember, positives point away and negatives point towards. So here, we have two vector lines pointing to the right, which leaves us with a net vector going out this way. Okay? And that happens all throughout this field, so that what we end up with is a model that looks like this. It points away from the positive into the negative. Okay? And when we are up here, we get this curved shape, like so. And we get this curved shape, like so. Get this curved shape, like so. Like this. And then as we go out a little bit, kind of can create this sort of looking shape. Okay? But the important idea here is that the rules still apply. Vector field lines point away from positives and into the negatives. Now, the reason I want to go over the component method first is just in case, right? Just in case a problem asks you, like, why is this portion curved? Okay, why is that portion curved? Well, if we were to take a look at it from the positive and negative separately, we can see that the positive E field at this point, okay, will be pointing in this direction, up and to the left. I drew it really small. I drew it smaller because it's pretty far away from the positive charge, so the field vector is going to be weaker. But for the negative one, okay, because it's closer to the negative one, okay, it's going to be nice and long, like so. Okay, I kind of exaggerated a little bit. But if we take a look at these two vectors, the first one from Q1 that I drew is going up and to the right, and the second one that I drew from Q2 is going down and to the right. And so what we end up with is a vector field line that is going down and to the right, like so, down and to the right at that point. Okay, and so if we take a look at all of these points along here, this shape is just created by vector addition. Okay, so the very last thing that I want to go over is the formula for E-fields. Okay, and we're going to do this by looking at the derivation of the E-field formula. So a couple of very important things. Let's keep in mind that all formulas tell us something about the system. And so I wrote out a little statement there. I said E-fields tell us how other objects would interact with the charge producing the field. So if we break this down, we can see the word interaction. Now for us here in physics, interaction either means a push or a pull. And a push or a pull is a force. So I want to start off there. From the previous video, we learned that Coulomb's law requires two charges, Q1 and Q2, and they are separated by a distance r squared, and of course we have Coulomb's constant hanging out there in the front. So if we were to take a look at that definition in Coulomb's law, watch what I do by breaking it down by using a little model of the E-fields that we just drew. Okay, so if we have a positive charge here, okay, we can say that that positive charge has a E field going out radially outwards, like so. All right, now let's say we put another positive charge along this E field here. And the question is, what will happen to that new positive charge? And according to Coulomb's law and the fundamental law of charges, that charge will feel a repulsion away from the primary charge. And the way that we can know this by the field model is that the positive charge will go along the direction of the E field vector. So if I were to draw an E field vector here, okay, notice that the field vector is pointing up and to the right, and the positive charge will also move up and to the right. Okay, now let's compare that to, like, let's say a negative charge. If we were to put a negative charge here, that negative charge will feel a attraction force up and to the left. Okay, so negative charges go against the field line, and positive charges go with the field line. Okay, that's very important. Positive charges go with the field line, and negative charges go against the field line. All right, so with that being said, and if we were to take Coulomb's law into consideration, we can actually derive the formula for a E field. So we know that these two charges will exert a force on each other, but if we only wanted to see how one of the charges feels anything, let's say Q2, I'm going to take Q2 out. Okay, so if I take Q2 out, I'm left with K Q1 over R squared. Now, just so you know, this R squared is the separation distance of Q1 from Q2. So what this one tells us is how will Q2, okay, experience a force based off of this mess in here. Okay, and this mess that we have in here, that is the formula for the E field. So what this means is if Q2 is in a E field, Q2 will feel a electric force. It's a nice little formula that we got there. So the formula for a charge feeling an electric force, all we have to do is multiply by the E field. Okay, so what I'm going to do here is I'm going to write a little statement, because the formula and understanding what the formula represents is just as important as the formula itself. All right, so let's put that there. All right, so if we have a charge within an E field, that charge will feel a electric force. Okay, so this is the statement that we can apply to the formula where I highlighted everything up here. Okay, so if we have a charge, which is Q2, within a E field, okay, and this E field is produced by Q1, right? Q1 is producing the E field, and Q2 is a distance R squared away from the E field. Q2 will feel a electric force. Okay, and a simpler way of writing that is that formula there. All right, so now that we broke down Coulomb's law just even further, we can now come up with the formula for E field. So E field is Coulomb's constant, Q, which is the charge producing the field, and all divided by R squared. So if I were to come up with a statement, we can write it like this. Charge Q produces a E field at a distance R. Okay. Boom. So that's what the E field formula tells us. So if I were to break it down by doing a drawing model, okay, that Q right there is right here, that Q. And if I were to look at a distance R away, so here, R, based off of that formula, it can tell us what the E field will look like. So if this were positive, we would have an E field pointing out radially this way. Okay, and the magnitude of that vector can be determined by using that formula. All right, and the very last thing that we want to go over, of course, are the units. The units for the E field is a Newton Coulomb, and we get that by using the F is equal to QE formula, right? E is equal to F over Q. The units for force is newtons. The units for charge is coulombs. So the units for E field is a Newton Coulomb. All right, that's it for me. In the next video, we will go over a couple of the mathematical applications of the E field formula. See you next time. Bye-bye.